Good afternoon, everyone. Welcome to the ISE webinar. I'm Sharon Volman, Editorial Director of ISE Magazine and ISE Expo. Thank you so much for joining us for today's webinar, Blown Fiber Deployment Within MDUs, presented in partnership with Hexatronic. In this webinar, you'll learn how air-blown fiber, or ABF, can provide an efficient, cost-effective means of deploying fiber within MDUs. By utilizing OSP and indoor rated microcables, a pathway is created to each individual living unit with a direct connection back to the fiber distribution hub. This design eliminates multiple connections, splice points, and allows for the placement of the FTH up to 1 kilometer from the ILEU. ABF is installed at 100 meters per minute, which far exceeds the speed of traditional methods of installing fiber by pushing or pulling cables through ducts. Please remember, just a couple little housekeeping things. Please remember to renew or subscribe to ISE Magazine to stay informed in this ever-changing industry. Get your own copy, print or digital, and you just click on the information tab or go to isemag.com, subscribe today. And don't forget about your 24/7 resource, the online ISE Buyer's Guide. We've gathered and categorized the latest fixed and mobile products to make your job easier and your networks better. So remember to check out isemag.com, isebuyersguide.com. Now let me tell you about today's webinar. It is brought to you by Hexatronic US. And that company is part of Global Hexatronic Group, which offers a wide selection of fiber system solutions and products for FTTH, metro, access, and submarine networks. Hexatronic enables non-stop connectivity for communities worldwide. They partner with customers across 4 continents, from telecom operators to network owners, offering leading-edge fiber technology and solutions for any and all conditions. Now, let me welcome our presenter. Joining us today is Roger Vaughn, VP of Engineering. Roger, welcome.
Thank you, Sharon. I appreciate it.
You have an extensive background in fiber optic cabling, connectivity, hardware. In the past couple of decades, you've worked with customers deploying FTTX. As a VP of Engineering for Hexatronic US, Roger works with customers defining solutions for deployments of optical networks from the central office to the living unit. And I learned this. Roger has 23 patents, which is pretty impressive in our industry. So for all of you watching today, we recommend that you watch in full screen mode for the best visual quality of the presentation. You can do this by clicking the 2 outward arrows at the top right-hand corners of your screen. The information tabs at the top of your screen will allow you to find out more information about our presenter, Roger, and our sponsor. You can also download a PDF of the slides from today's presentation from the Additional Resources tab. Finally, we want you to get involved, so please submit questions throughout the presentation using the Ask a Question tab on the left. I'll hold the questions until the end of the webinar, at which time we'll answer as many as possible. Great news that you'll receive 1 BIXI credit for attending this live webinar in its entirety. The credit is also available for recorded webinars. The certificate with the BIXI credit will be presented to you at the conclusion of the webinar, and a link to download it will be sent to you at the time as well. Now I'm excited to share with you, Roger, welcome, and thank you for joining us.
Thank you, Sharon. I appreciate it. Let me drop down. Oops. Make sure I get the right one. Okay. Thank you, everyone. Appreciate you coming. Good morning, afternoon, or evening, depending on where you're at. Want to introduce you today to air-blown fiber solutions for MDUs. And this is based on a study that we did on a MDU complex that was actually built out with fiber, splice in place cable solution, not ABF, but looking at it and studying it to see what what we could gain from our experience and what was a more efficient way possibly of doing it. We even re-engineered the splice in place cable solution to see if there was a better, more efficient way of doing it than it actually was. So we're going to take a look at some of the what ABF is, what those components are that we're going to be talking about going into this study, and the solution that we put forward. And then we'll take a look at the MDU, the type of MDUs that we're looking at, and then into a little bit more into the overall layout, network design of the MDU, kind of overhead view, and zoom in a little bit, some of the different components. And then we'll end up, of course, the meat of the situation that you want to see is what is the actual cost and what savings can be generated using air-blown fiber solutions. So let's go ahead and get started here. Next slide. So, as I mentioned, we're going to go through and define a few things here. So air-blown fiber unit. Air-blown fiber consists of air-blown fiber unit. And a lot of times we associate air-blown fiber with cable. There's air-blown fiber cable, but this is air-blown fiber. Air-blown fiber unit consists of a grouping of fibers surrounded by an acrylate coating, as you can see here, and then a thin oversheath, which is a low friction oversheath, allows it to slide through the microduct quite easily. The typical configuration here for the drop to the actual individual living units is 2 fibers. We group 3 actual units together, the one being a strength member, but is actually a fiber. It's a mechanical fiber. So that black one in there is an additional fiber, excellent strength member, has the the tensile strength of 800,000 kpsi. Really can't get better for a strength member. So two actual optical fibers, then what's called a mechanical fiber, make up the fiber grouping, acrylate around it in the jacket. Now we have between 2 to 24 fibers that you can pass through this microduct. 2 through 12 is 250 micron. When you get to a 24 fiber version, we drop down to a 200 micron fiber. Allows us to still maintain a very small diameter of 1.6 millimeters, but able to get 24 fibers. Now, why would you need higher fiber counts? Well, those aren't for the individual living units. Of course, we're just going to use those 2 fibers for the individual living unit. The higher fiber counts are for that distribution to the individual FDHs within the network, within that complex, or sometimes within neighborhoods, but this is within the MDU complex that we're talking about today. So connections between FDHs will use some of those higher fiber counts and blow from one FDH to the next, but individually to each unit, that would be the 2 fiber. Over on the right, you can see a 2 fiber being installed from a home back to an FDH, and that's at full speed, 100 meters per minute. And the unique feature of air-blown fiber is we can blow that up to 1 kilometer. It's very rare that we have a home that's over 1 kilometer away from the FDH, but that is a capability, typically more in that 1,200 feet range, 1,500 foot range. Air-blown fiber units can be pre-terminated. These solutions have an inside in, of course, and you can put those on reels. You can have a SC or LC connector on the inside in. On the outside in, there is a unique feature here that the fiber can be terminated with a LC ferrule. And, oh, sorry, I was looking at the presenter chat there real quick. LC ferrules, 1.25 millimeters in diameter, of course. A little bit of a crimp ring in between the air-blown fiber unit and the ferrule. That brings it up to around 1.5 millimeters in diameter, not too large. The duct that we are blowing through, the dimensions on that are 7 millimeters outside diameter and 3.5 ID. So even with a 1.5 millimeter OD with that crimp ring there, you're still well within the range of the ID of the duct that we're blowing it through. Once that ferrule is blown through you simply snap together the individual pieces, and you have an LC connector on the outside end at the unit itself, or at the FDH, whichever one you're running it to. So a little bit more information on air-blown fiber. So I get this all the time. You're blowing the fiber. There must be like a parachute or something on the end, and the air is pulling that fiber through the duct. It's actually not true. We're pushing the fiber through. Within that air-blown fiber tool that you saw earlier, with the spinning reel, there are a couple wheels or a track that's pushing that air-blown fiber unit, and air is assisting the fiber being blown into the microduct. The air is there to help levitate the fiber unit and help it from interacting with the sides of the duct, increasing friction. So air just kind of eliminates that frictional component, and we're just simply pushing that fiber down the microduct. Duct size, you want to match that. Obviously, you can't have too large of a duct to do this with. Inch and a quarter duct, it really wouldn't work. So you have to have a small duct size match up to the small fiber unit. And of course, if it gets too small, you wouldn't be able to get enough airflow, and you would encounter that frictional component and slow it back down as well. For the outside plant, the distance from the FDH to the building itself, before we transition to go to inside duct, you're going to use an outside plant duct. And that comes in many configurations. Mainly what we're using for this study is 12 and 24 groupings. So you'll see here on the lower right-hand corner, you got a 12 and a 24 grouping. 24 works out quite well because this particular study, the individual buildings were either 24 units or 36 units. So one of the 24s and one of the 12s, or just one of the 24s to feed the individual buildings, worked out quite well. And that's typical for that garden style type of apartment complex. Now, the one-way ducts you see here, that's typically used as the final drop. In this installation, of course, we're in an MDU. We're going to have to change to a riser-rated duct, which we'll go over in a second. So that outside plant one is more applicable for single-family units, but that's typically the last leg of the deployment from the multi-duct. Then we branch out and go to the individual ducts, and you'll see that here in a second. One of the items to note, and I'll note it again here, is we simply have connectors placed in between the ducts to transition from one duct to the next, or from a multi-duct transitioning down to a smaller one-way duct. It's simply a connector. So and I'll go over this a couple times. The concept here is with air-blown fiber, we're providing a pathway first from the FDH to the living unit, and then we're blowing that fiber in. So duct is placed first, no fiber at all on the install. And one of the great things about microduct is the repairability of the duct. It's simply repaired with an extra piece of duct and connectors. There's nothing really else that needs to be done there. Simply cut out the broken piece or damaged part, and connect it back together, and you're as good as new. For the inside plant, of course, there's regulations and requirements to have a flame-rated product on the indoor spaces. So at the building, we will transition from outside plant duct and HDPE material, which is obviously not flame-rated, to a riser-rated product. This one happens to be a halogen-free flame-retardant polyolefin, riser-rated, so it meets all our NEC requirements, and has all the same attributes as the outside plant. One unique feature here is that we've reduced the size of the product in using 5 by 3.5 millimeter ducts on the inside. So that reduces the amount of material, reduces the amount of flame material within the building. It's both sustainability and also to help with the flame rating. The one way that we're going to utilize in this study is actually a 7 millimeter duct with a inner 535 millimeter duct. What that allows us to do is use it in configuration of the 7 with the 3.5 ID. We can simply transition from outside plant directly to the one-way. So 7 millimeter outside plant, 7 millimeter inside plant, and directly transition within the building itself. The other major component of the ABF solution is what we're calling a regionalized FDH. It's a smaller size FDH than you would typically see in a large centralized split, where the splice in place cable solution used a centralized split with a 288 fiber cabinet. This is a smaller cabinet, and we regionalize it so that it is placed within 3 to 4, maybe 5 buildings, and we deploy from that FDH to those individual buildings. And when we get into this a little bit further, you'll see that the costing and reason for that, it makes much more sense to do it that way than to have the centralized point where your length of the duct that you're installing is quite a bit longer. To keep the cost down and to minimize the amount of material that's being deployed, the regionalized approach works quite well. So you'll see FDH for the ABF solution is going to be more of a smaller FDH, smaller count for FDH, and that can be either underground or in a cabinet style, just like any other FDH out there. And then, of course, at the individual living unit, we're going to have a fiber terminal box. You may have a smart panel as well. Being new construction, a lot of times we have smart panels. In those smart panels, there's an ONT, and a lot of times there's already fiber management with that ONT. So in that case, we would just run simply to the smart panel, use the fiber management that's in there, and we'll skip the fiber terminal itself. But if that is not there, then the fiber terminal can be used. That can be placed pretty much anywhere within the house, mounted directly to the wall at the outlet height, at the media center area, or a lot of times in new construction, we're at the master bedroom closet. So that can be placed, terminate the fiber there. When service is called, they simply jumper over from there to the ONT. Some of the unique tools that are used for air-blown fiber, there's not many. The main thing is some of the duct cutters and duct access tools that we have. There's a sheath removal tool and micro duct cutters, and it's very important that the ducts are cut cleanly so that when they're inserted in the connectors, there's no burrs or edges that might impede the air-blown fiber unit from passing through. So it's always good to have good sharp blades and make sure that those are cut correctly and installed fully so that there is no edges or anything to impede the flow of the air-blown fiber. And of course, when you need to access the fibers, we have a stripping tool for that air-blown fiber unit, and you've already seen the air-blown fiber tool kind of in use and how that's done. All right, so let's get a little bit more into the air-blown fiber, the MDU that we use for this study. So it's what's called a garden-style type building. 2 to 4 story buildings are typical, and 8 to 24 units, maybe a little bit more, maybe a little bit less. But that's your typical size. And we see these throughout the Southeast, Southwest, West. Not as much up in the Northeast, some of the older high-rise buildings there, but this is quite popular style, and this is the reason we did it on this style of building is because it's so popular. It's quite prevalent in most areas. Now the networks, any style of network can be deployed. The one that we're looking at in this study is a GPON network. So PON, point-to-point, Ethernet, any of those networks will work with this solution. But as I said, we're using a GPON network here. Damage to any of the ducts during construction or after construction, easily repaired. You're repairing that duct at that point of damage. You're not having to pull out the whole duct and put in a new duct. It's just there at that one location. So really there, and during the construction phase, there's no fiber in those units either. So there's no fiber cuts being made. Whereas a splice in a splice in network where you're splicing the cables in, those cables have been deployed. You're splicing in vaults and enclosures. You may not have deployed within the apartments yet, but you've got ducts in there. You've got cable running to the unit. So there is the possibility that the cable could get hit and damaged. And actually in this particular study, the property that was actually installed, how it was installed, one of the cables did get hit by some of the construction and had to be repaired. So much cleaner and easier repair methods for their ABF solution. This install or study was 100% take rate. We looked at providing fiber to every unit, just so we had a comparison 1-to-1. The actual install was success-based, which actually plays quite well with the ABF solution, in that fiber from the FDH to the living unit is never deployed until service is requested in that instant. So if you're looking at saving some money during the deployment so that you don't have to invest in fiber until it's actually absolutely necessary, at least the fiber from the FDH to the unit, the ABF solution allows you to do that. You just proof in your pathway, you're ready to provide service when it's needed, but you don't have that fiber sitting in the duct waiting for a customer to request service. It's only placed when you need it. The other great thing about we found in the study, and we find in many deployments, is the ABF solution eliminates many of the closures and handholds, because we're just doing a pathway. We're not looking to splice in higher fiber counts and distribute out lower fiber counts from a handhole or vault, pedestal, or any of the wall boxes as well. So looking at the greenfield solution, and that's basically what this study was around. So all the trenching and everything, that was all open trench in the study. So all the placement of duct and cables pretty much the same. It's really looking at the different techniques of deploying, whether ABF or splice in place. So your microducts are installed during the construction. The FDH to the fiber terminal box transition from the outside plant, and I'll go over what I mean by transition, because it's not really a thing or item. It's just simply going from one type of duct to another. It's not it's using a connector. It's not a actual box or anything. The region, as I mentioned, the regionalized FDHs will feed 3 to 6 buildings, give or take. And that eliminates the need for a demarcation at each building. So a lot of times there's a point where you have to transition at the building from the outside plant to the inside plant. This is eliminated in that we're just doing that transition with connectors. And then we take advantage of the installation distance of the ABF units. We take advantage of that up to 1 kilometer length and 100 meter per minute install speed. So even if we're 600,000 feet away, it only takes a few minutes to blow an ABF unit from that individual living unit back to the FDH. Very quick process. And then you just simply go from each living unit and blow back to the FDH, and then do all your connectorization in one place at the FDH. Very, very simple process. The alternative to that, as I mentioned, is you have the terminal on the side of the building, and you're pulling cable to each living unit, and that takes time. But then also you have all that splicing on the side. We'll go over that in a little bit as well. But there, the ability to blow the fiber up to 1 kilometer is very advantageous in the MDU environment. So as I mentioned, a transition. What is exactly the transition? that is simply going from one duct or a duct assembly to individual ducts. That is simply done here, going from outside plant to inside plant. That's the transition point that I spoke about. And that is, just this. There's nothing really else to it. This can be placed in a telco closet. We've seen it placed in walls. So it's just a direct connection between the outside plant and inside plant. Again, here, outside plant to the rise rated inside plant. On a multi-duct assembly, you may have need to break out some of those individual ducts and then route those to individual apartments. So this is what's called a duct access point. And we're simply taking out the individual ducts using what's called a reduction connector, because we're going, remember, on the riser rated, the multi-assemblies, those are 535 duct. And then we're going to the 7 millimeter one-way within the individual living unit. So here it's called a reduction connector, 5 millimeters to 7 millimeters, simply transitions from this point into the single ducts. All right, so let's get into the example study here. So as I mentioned, this is a real complex that was built out with splice-in-place cable. It was done a couple years ago. The property was, greenfield at the time, so all open trenches. Everything was fairly low cost as far as placing the duct, placing cable. It was done in such a way that it ended up costing, right around $1,000, a little over that per unit. Just keep that number in mind. And the actual installation pathway that was taken was a little less optimized than you would want. What we did is we took a look at a more optimized method of doing it with splice-in-place cable to give us a true comparison to the air-blown fiber solution. We didn't want to, take a solution that had some deficiencies to it and compare it to our optimized solution of ABF. We wanted to take an absolute best case scenario of a splice-in-place solution and compare that to the typical ABF solution, how that would be deployed. So we have apples to apples comparison versus what was actually done. So for the Greenfield MDU, and this is our optimal splice-in-place solution, you would have a centralized cabinet or centralized telco room, and that is here in the center of the complex. And then out from that, multiple cables are taken. So in red here, that's a 144 fiber cable to a splice point. This splice point, you have a 24 fiber cable coming out feeding this building, and then a 48 fiber cable coming out and feeding this building, which is 36 units. So you have 24 unit buildings and two 36 unit buildings here and here. The rest are 24. We're also dropping off fibers at the clubhouse, and a maintenance building as well. So splice points, you'll see several of those anywhere you're going from, a 48 or 24. There's a splice point there, splice point here. So these are multiple splice points throughout the complex. The one part that we did not include in this study is the fiber from the curb to the centralized cabinet. Just so it kept everything apples to apples. We went from the FDH to the individual living unit and compared those two numbers and strategies of how to deploy that network. Take a little closer look. As I mentioned, the red in this diagram is a 144 fiber cable. The blue is a 48 fiber cable, mid-span access here in this closure, and dropped off 24 to this building. The other 24, of course, drops over to the adjacent building. Here, dropping out with a 24 over to this building. If you look closely, you can actually see the actual handhole right here. This is the splice point that was used for the actual install. So this 144 came over to here. Optimally, that's not the best place to have it. You don't want to run your 144 additional feet. That's not needed. So putting it back over here, we used less fiber to deploy. So little things like that we optimize the design. So again, we want to make sure that we're comparing apples to apples, the best design scenarios of both. And we were very conservative in doing so that, we had a true look at what this is going to look like cost-wise to the end user, the ISP. So then we looked at it from an ABF deployment, and what does that look like, and what's the most optimal design there? As I mentioned, we're going to use regionalized FDHs up to 96 count, and we're going to deploy between those FDHs a higher fiber count ABF fiber, and then from the FDH, we'll deploy to the individual buildings, transitioning to the riser rated duct within the building and to the individual living units. So here you can see these little squares with the X's. That's the regionalized FDHs. So there's 4 of them in this plan. The green lines indicate where we're connecting those FDHs together. So the fiber from the curb is fed to this first cabinet. We then blow, in this case, I think we designated a 12 fiber to this FDH, dropped off 3 fibers, then to this FDH and dropped off 3 fibers. Same thing over here. We blew over to this location, and we got 3 fibers dropped off at this terminal, or this FDH. And then of course at the curb here where the fiber came in, 3 fibers were dropped off that FDH. Now those fibers are dropped off and then connected to splitters. So in this case, 1x32 splitters is the design. And from there, then we deploy the 12-way and 24-way microducts to the individual buildings. In this case, the red being the individual 24 multi-ducts to the building. And then at the building, there's a transition point. So you've got the little rectangle with TP in it that we're transitioning to that riser rated duct, deploy it throughout the building to each individual living unit. And that creates that continuous pathway. So now we have a pathway from the individual living unit all the way back. A little closer look up at that. So again, these are the FDH locations, 24-way in red, and the green being the duct where we connect the FDHs. This being a single duct, so a single 735 duct. Keep that in mind. Very small duct placed in the same trench right beside the 24-way, so that we can access or gain access to each FDH and supply fiber to those splitters. Transition points, indicated here. Again, I didn't draw in all of the individual drops to the units themselves because we've gotten a little bit too much here in the drawing, and would have been a little too messy to see. But from this point, you get the individual drops out. ISP duct installation, what that looks like, it's not really a whole lot to it. Everything is brought back to a centralized point, whether that's a telco closet or a mechanical closet of some sort. In the ABF model, we're transitioning. That's all we're doing at the side of the building. So we're going from that outside plant duct to inside plant duct. Whereas with the splice in place model, what was actually done on the property and what we did in the idealized design, you have duct in the apartment building, and that's run to a telco closet to a terminal. So this terminal is where we're transitioning from the outside plant cable to the inside plant cable. So individually, these ducts are a little bigger than the 7mm ABF ducts, 12.7mm versus 7mm. The individual ducts carry a cable. Cable can be included in the duct during the installation or pulled in afterward. Either method is about the same when we look at cost and the waste amount of material that comes off of it. So not a whole lot of difference when we did the analysis there, but the speed at which these are deployed is quite a bit slower than the 7mm ABF deployment. And then of course at each individual building, 10 buildings in this case, you have a terminal and you're splicing within that terminal, either a direct splice, or in this case, this was connectorized so that they had a test point per se in the building itself. Not necessary because the FDH is not that much further away. So really no need to have this additional component, and you'll see in the numbers the cost of having this in here is significant. So not only splicing, but then also the physical equipment itself. Really no need. It's much simpler just to have a transition point. So the major differences in construction, I think this slide's pretty much sums up why we saw such a cost difference in the deployment methods, and why we advocate that an ABF solution for your MDU is going to be more cost effective. You have 4 points, fiber termination box, both locations. You have riser rated one-way duct from that fiber termination box in both scenarios here. But after that, that's where things change. So we've got a transition point, just continuing that pathway on through to the outside plant, all the way to the FDH and the ABF solution. When you look at a splice in place cable with a centralized split, you're going to have a terminal to transition from the outside plant cable to the inside plant cable. This is either a splice point or a cabinet such as this with patching. And then when you're going from a distribution cable, so one of those 24 or 48s that's branching out to the individual buildings, you're going to have to splice that into the main cable that's going back to the FDH. There's going to be a splice point and a vault. So 2 components here that are fairly costly items and take up some real estate, and quite a bit more splicing involved in getting the outside plant cable routed back to the FDH. And then of course the FDH is a much bigger FDH, and cost-wise the FDH, the centralized FDH, is comparable in price to the individual FDHs, where we use 4 in our example. So let's take a look at the numbers. I think that's the big comparison here. And we look at the cost comparison between splice in place versus the air-blown fiber solution with the regionalized FDHs. Whoops. So this is on a per living unit basis. So the ABF regionalized FDH versus splice in place. Let's take a look at the outside plant first. And there's some notable differences here. On materials, we don't see a whole lot different. It's duct and duct that we're installing. You're going to have to place duct to pull cable. You're going to have to place micro duct to blow ABF. So not a huge difference. A little bit of savings per unit. It adds up over 264 units, of course. The big difference here is in labor. So there's quite a bit more splicing involved in the splice in place solution. As I mentioned, you've got the vaults and splice closures. You've also you've got the terminal at the side of the building where you're doing the outside plant splicing in there as well. So no surprise here, over twice the cost on the labor. You've got a lot more going on here. When we look at the inside plant, your materials, significant difference here. That terminal placement and splicing, that's where that is incurred. You're going to see a lot more costs there, right? Now, when we look at the labor, labor actually went up on the ABF side versus the splice in place. Now, splice in place, we're only doing the short distance from the fiber terminal box or the ONT to that terminal on the side of the building. Whereas with ABF solution, we're going all the way back to the FDH. So we would expect a little bit difference. So nominal difference here around $28 or so per living unit on the labor, but that's expected because we're doing more. Okay. And then when we look at the total cost comparison per living unit, and also added in the totals for this. And again, this is from the living unit to the FDH, not any of the other outside plant construction to get to the complex itself. We total up $439.83 with the ABF solution. That's all in with labor and materials, where the splice in place cable centralized split came in at $623.15. 29% cost savings. It's a significant amount of money when you're doing multiple MDU complexes, multiple building, multiple thousands of units per month. It can add up quite quickly. So that's the what it boils down to is it's a lower cost solution. It eliminates many of the splice points and points of failure, to be honest with you, that are inherent in splice and cable design. So the ABF provides that pathway. You're blowing the fiber when needed. In this case, we did 100%, so we had apples to apples. But in a success base, you're just not investing in that fiber until it's actually required to provide service. So that's a big benefit to keep in mind. So 30% cost savings in this study, and I would be happy to go further in depth with you if you'd like. We can break these numbers down further, but not enough time in this presentation to go into individual, the different techniques and different components, but would definitely entertain speaking with you individually if that's what you'd like to look at. All right, and with that, I am pretty much done with the presentation. We'll go ahead and take some questions if there's any out there.
Yes, we have some good questions.
Great.
Okay, I'm going to start at the top. Does the pre-terminated with a ferrule version affect the blowing length?
No, it does not. So the ferrule, as I mentioned, is 1.25 millimeters in diameter. With the crimping on there is around 1.5, but we're blowing into a 3.5 millimeter duct. So we have plenty of room. The ferrule itself, we want to make sure the pathway is clear, and we have what's called a test dart that is basically the same length as that ferrule. So when we verify the pathway is good to install the fiber, we'll blow one of those darts if we're using the pre-terminated solution, just to double ensure that it's going to pass through. Because last thing we want to do is blow a pre-terminated solution down and there's some mud or something that wasn't detected or didn't get cleaned out, and it causes damage to that ferrule. So there are some things that we can do to verify the pathway, and there's no issues with it. But yeah, there's no issue blowing the ferrule the full kilometer.
Thank you.
Mm-hmm.
Question about standard. Does the product have a standard rating for use on DoD bases?
Department of Defense. That's a good question. There are, I know of several deployments that are shipboard, and it's not something that I have personally been involved with, but yes, the DoD is well aware of ABF and has been deployed on several bases, and and we're involved with a project now that is indirectly with the DoD, and we will be providing fiber to the home services on a Army base here in the U.S.
Very cool. here's a question. During the blowing of the fiber, how many turns can it handle?
That's an excellent question, right? It's a little nuanced. So we typically say 990s, and that's you can take up to 990s and you can get that type of performance. Now, how big a 90 is it? Is it a very tight 90, to the minimum bin radius, or is it a large sweeping 90? That would make a big difference in the distance that we can blow. I would say that 990s is pretty, a very cut up building that you might be running through. It's hard to get that many 90s, but you try to stay, above the minimum bin radius. And the more you stay above that minimum bin radius, the more to the distance that you can blow. But in just as a rule of thumb, 990s.
Thank you.
Mm-hmm.
This is a good one. What is the service life for the microduct couplers? We have a steam tunnel environment and wondering about water and long duration elevated temperatures, 100 degrees Fahrenheit, and exposure to temps to 130 degrees Fahrenheit.
Well, that's another good question. There are various, just like anything, there's various types of connectors for various different applications. And we have some that are, the gold standard that can be placed pretty much anywhere. They are suited for extreme environments. And then we have the run-of-the-mill outside plant that is suitable for fairly high temperatures. So it just depends on what your application is, what your spec is, and then those connectors can be adjusted. We can look at the different types that are available and pick the one that's more appropriate for that application. All the connectors are 100% watertight. This is no different than you can run down to Home Depot or Lowe's and you have the little quick connect connections. It's the exact same type of connection. There's an O-ring in there, seals the duct to the connector. There's no leakage in the field.
Thank you. Another operational question. What's the expected life for the ABF ductwork? Should the duct still be usable in about 20 years? Time to permit the replacement of the fiber if the fiber application changes? And then again, another question about the couplers. Would the couplers be the weak point in the system? And if so, should they remain in a service accessible area?
No, we direct bury. I'll answer that question first. So the connectors are direct buriable. Again, they're meant to be direct buried. They're 100% sealed once connected. There's really no need to go back. Some customers will put a locator ball or some way to locate that point if they, in the future want to go to there and for whatever reason. But we expect it to last the lifetime of the duct. The duct is manufactured out of the same exact material that any other duct that's employed in your network today. So standard 1.25 inch, 1.5 inch, 2-inch ducts, exact same material. So we expect the exact same lifespan with any of our micro ducts as we do with any of our larger ducts. It's the same process, same materials.
Thank you. How do you clean a dirty duct?
A dirty duct, yes. So
not a dirty duck. And
I'm assuming the inside, right? So yeah. During installation, you want to keep the ducts capped. So we have just simple caps to put on the duct to keep moisture and debris from getting into them. But inevitably, you're going to get some sand. You're going to get some moisture buildup in there. If the cap is left off, these ducts are in the ground. The ground temperature is 55 degrees typically. And if it's hot outside, hot and humid, you get that little bit of air movement in there. You're going to get some humidity. You're going to get some condensation. You'll inevitably get some water in there. So prior to any installation and prior to turning over the construction phase of a ABF deployment, we use sponges to blow out a duct. So even in the 3.5 millimeter, we have a very small sponge placed in, and air is blowing at one end, and that duct pops out the other end very quickly. And we take a look at that sponge to see if there's any discoloration or any if it's soaked up any water or anything. And then we verify that the next sponge that comes through is clean, or we blow, continual another sponge until we get a clean sponge comes out. Then we cap those with end stops, which are watertight seals. So when we're ready to deploy, we cut those off and we can deploy the fiber knowing that we have a clean pathway, and there will be no issues with it.
Thank you. In this particular case study, was the trace wire installed separately with the ducts, or is there a trace wire built in for the purpose of damage prevention?
So tracer wire is included in all the outside plant ducts. We do not place a trace wire in the riser rated ducts. There's no need to trace or it's nearly impossible to trace, obviously, within the building where that actually went. So yes, in the outside plant, every duct that is placed in that environment has a internal tracer wire with it.
Thank you. Speaking of risers, how many meters can you blow up in the riser ducts?
You can blow up a good distance. However, that's not what we recommend. Gravity is always your friend, and you want to blow, whether it's in a single family neighborhood. If I'm at the top of the hill, I want to blow downhill. Same thing in MDU. If I'm at the fourth floor, I want to blow from the fourth floor down. I don't want to blow uphill. Yes, we can blow uphill. It's not something that we quantify, but it is possible to blow, up and over hills or up a floor or two. But it's not something that we recommend. You definitely want to use gravity as your friend and blow downhill if possible.
Makes perfect sense. Let me see here. Question about the pricing. Was the price comparison including labor and materials?
Yes. So we broke out labor and materials. And as I mentioned, we tried to be as conservative as possible. We did not want to be unfairly judgmental of the splice in place cable method versus the ABF solution. As I mentioned, this study was of an actual complex that has fiber in it. And the way they did it was a little different and was not optimal and was slightly over $1,000 per unit. So our analysis, optimized our design, and we came down to 638. So we tried to be equal, right? We tried not to play favorites.
Makes sense. This is a good one. This person says ABF solution is good for greenfield ISP installation, but for brownfield, I can imagine a nightmare with inhabited MDUs with older infrastructure. What are your thoughts about that, Roger?
Well, my experience is every MDU is different. So it is possible to get ducts into older MDUs if the space is available. If we can place duct, there's no different between a brownfield or a greenfield in that case, right? So if ducts can be placed into that brownfield solution to the individual living unit, then we're going to blow a fiber just like we would a greenfield. There's no difference whatsoever. Each MDU though has its peculiarities to it. So if it's already built, you're going to have to find that pathway, and sometimes you can't get duct through there. So there's some other ways that you're going to have to approach that MDU. I could do a whole presentation on how to access MDU. So it's a long question to answer, but if ducts can get into the brownfield MDU to the individual living unit, then there's no difference, really no difference at all.
Good answer. We are starting to run out of time. A really good question. What's the best way to contact you for evaluation of my particular project, and what are your lead times for materials? Okay.
That's more a commercial question, and I would the second half of that question I'll entertain that individually when we talk to you about it. You can contact me. I think all the information is on the webinar, So you can contact me directly, or you can go to hexatronic.com and click on the US, and all our contact information is in there as well.
Fantastic. Roger, that was very informative and very well done. Thank you.
Thank you. Appreciate it.
It was my pleasure facilitating it. And it was a pleasure having you all take some time out of your day to join us.
Yes, thank you.
Yeah, for sure. Please continue to visit ISE Mag for information on upcoming webinars. We want to thank Hexatronic for being our sponsor for this one. Thank you all for taking time to invest in your professional development and continuation of learning, and have a great afternoon. Bye-bye.
Bye. Thank you.